Okay guys, welcome back to PChem. Welcome back to our discussion of the Gibbs energy, and where we left off with was finishing up talking about fugacity. Okay, these are the last few things. We're just tying up the loose ends before we get into a thermodynamic description of chemical equilibria. Okay, so that's coming up in the next chapter, and we just need to finish off, tie up a few loose ends before we move on. Okay, so we just talked about fugacity and what it actually means. Fugacity, if you remember, is equal to phi times P, okay, where phi is this fugacity coefficient and pressure is the pressure of a gas. So fugacity is simply the scaled pressure of a gas, and it is the proper way to define the pressure of a real gas, okay? But then the next question becomes, okay, great, but how do we measure this? Okay, how is this measurable? We know how to measure pressure, but how can we measure the fugacity coefficient? How can we measure that? Okay, but to start, to start out, we wait a minute. Wait, do you guys hear that? Or is that just me? Is that just on my end? Wait, what is that? What? I don't quite. Oh! Been successfully rickrolled today. Don't forget, it's April 1st. Bet you didn't even see it coming. Okay, after that excursion, let's get back to the actual reason that we're here, which is talking about physical chemistry. Okay, so get your minds back into thinking about fugacity and what it actually means. Okay, we want to know how to measure fugacity. How can we find this experimentally? Okay, if we look at the infinitesimal change in G, this is equal to negative S, or negative entropy, times the infinitesimal change in the temperature, plus the volume times the infinitesimal change in the pressure, plus this new term that we just defined here that has to do with the chemical potential. So the chemical potential for each of the ith components times the infinitesimal change in that ith component's molar quantity. Okay, so if we say that, let's try to simplify this a little bit. Okay, so we have let's say for a single component, okay, so we only have one I here, single component, and let's also make this isothermal. This allows us to take away this portion here. So when it's isothermal, dt is equal to 0, and we can say that dg is equal to v dp, so the volume times the infinitesimal change in the pressure, plus mu times dn. Remember, we only have one single component, so the sum just becomes one thing, okay? And because dg is an exact differential, remember that, it's an exact differential, so it has a bunch of rules that it tends to follow, and because of that we can explicitly write the partial of mu with respect to the partial of p is equal to the partial of v with respect to the partial of n. Okay, this is using the cyclic rule, of partials to get this term here, okay, or to get this expression here. Now this part on this side is the change in volume with respect to the change in the number of moles, or the molar quantity, okay, and this has a special name. This is called the partial molar volume, and we're going to give it a symbol of V hat. Okay, so we can say that the change, or the partial change with respect to the chemical potential of the chemical potential with respect to pressure is equal to the partial molar volume. Okay, and for an ideal gas, sorry, I'm skipping ahead. Now we're going to take the partial of P and move it over here, so we end up with the infinitesimal change in the chemical potential is equal to the partial molar volume times the infinitesimal change in the pressure. Okay. For an ideal gas, we're going to write this as, and we'll get back to this in a little bit, and you'll see why I'm writing it out explicitly. So the ideal chemical potential is equal to the ideal molar volume times the infinitesimal increase in pressure. Okay. If we subtract the infinitesimal change in chemical pressure by the infinitesimal change in chemical potential, the chemical potential for the ideal case, okay, so we're just subtracting out the ideal from the real, what we end up with is V partial molar volume minus the partial molar volume of the ideal case times the infinitesimal change in pressure. Now, if I take the integral of both sides, okay, I end up with mu minus mu ideal is equal to the integral from 0 to p of V minus V ideal times dP. Okay. We can further write this as mu minus mu ideal is equal to, basically separating out each of these components, partial molar volume dP minus the integral from 0 to p of the partial molar volume for the ideal times dP. Okay. Now, recall from before. Okay, this was maybe last lecture, or maybe the lecture before. We defined the chemical potential as being equal to the chemical potential under standard conditions plus RT times the natural log of PF over PI. Okay. So if we define for the real case, we use fugacity for PF, and in the ideal case, we use pressure for PF, and we plug these guys in. We can form both a mu, so mu is equal to mu naught plus RT natural log of fugacity over P naught. Okay, the initial is P naught, and mu ideal is equal to mu naught plus RT natural log of P over P naught. Okay, now these two I'm going to plug back in up here. Actually, no, first I want to subtract them. Okay, so above we have mu minus mu ideal, so let's go ahead and do that here. So we have mu minus mu ideal, and this ends up equaling if we just plug these two guys in, actually, I'm going to go ahead and simplify this. I'm going to skip a step. If you want to go back and verify this for yourself, you're more than welcome to. This is going to be equal to RT times the natural log of F over P naught minus the natural log of P over P naught. Okay, that's what that ends up equaling. When you have natural logs or any type of log that subtract, you can, using the identity of logarithms, you can turn that into a quotient. So that becomes F over P naught divided by P over P naught. And in this case, P naughts cancel out, and we end up with RT times, times the natural log of F over P. Okay? And this is equal to mu minus mu ideal. Now this is a really simplified equation. All right? What I want to do is I want to take this and I want to substitute it in from way up here. I want to substitute it in up here. Okay, I'm going to substitute it in there, and I'm going to rewrite it down here. Okay, so substitute that back in for the expression above, and I find that RT times the natural log of F over P is equal to the integral from 0 to P of the partial molar volume times the infinitesimal change in P minus the integral from 0 to P of the infinitesimal change in the molar volume for the ideal case times the infinitesimal change in P. Okay, and we can actually just divide out RT from this side here, and so we get this whole thing times 1 over RT. And if you recall, F is equal to phi times P, right? So F divided by P is equal to phi, which is exactly what we have here. So we can rewrite this as F of phi is equal to this value here, okay? So we're directly able to, I'm going to erase this part here. You guys have seen it, okay? This whole thing allows us to experimentally determine the fugacity coefficient phi, okay? But it looks a little complicated. So what does it actually mean? What does this whole thing mean? Okay, we've got a bunch of integrals in there. You have to remember or recall that an integral is just the area under a curve. Okay, it's just the area under a curve. If you have some function, right? If you have some function and you want to know, for example, some function fx, we'll call it, and you want to know the integral between x1 and x2, the area under the curve is equal to the integral. Okay, so all of the shaded area here is equal to the integral. So the integral from x1 to x2 of f of x is equal to the area under the curve. Okay, that's all that an integral is telling you, is the area under a curve. Okay, so if we have, for example, the ideal case. Okay, the ideal case where we have volume and pressure here. Okay, and let's say that this is P naught. The ideal case shows this decreasing something like that, okay, up till P naught. So if we take the integral from 0 to P of the molar volume of the ideal case times dP, this is just the shaded region underneath this curve, all the way to P. Okay? If you look at the real case, let's do this in red just to make it easier. Okay. In the real case, you have some function that doesn't quite look like the ideal case. All right. You still have P naught, and you can still find the area under this curve. Okay, and this area is given by the integral from 0 to P of V real times dP. Okay, so this is the real case, and this is the ideal case. Now, in the above expression, we are simply subtracting the ideal from the real. Okay, so if we draw a curve that represents that, okay, we have the ideal case up until P naught, and then we have the real case, which looks something like this. Okay, so black is ideal, red is real. Oh, that's confusing. Black is ideal, red is real. Okay. Now the difference between these two. So from 0 to P V prime or V hat dP minus 0 to P of V ideal dP. Okay. You're just subtracting these two integrals from each other up here, and what you end up with is the area between the curves. Okay, just gives you the area between the curves. And so what you are proportionally measuring is directly proportional to the natural log of the fugacity coefficient. Okay, so that's all you're measuring in this case. It is simply the difference between the areas under the curve for the ideal versus the non-ideal case. Okay, and that's how you measure it experimentally. There are several examples in the book that you can go through and look for yourself exactly how that works out. Okay, I'm going to end it here. I know that this was a little short for today. Happy April 1st, but we have finished chapter 4, and I want to give you guys time to kind of absorb the content of chapter 4 before I jump into chapter 5 on Friday. So I'll let you go a little bit early today. I know that I gave you a lot of content, and I can move a lot faster in these virtual lectures. I know I can than what I would in real life. So I want to give you guys time to absorb all this information. Watch the videos as many times as you want. I will be posting, or as many times as you need to understand. I will be posting homework shortly, and that'll be due in about a week. Okay. And yeah, and also in the very near future, I will be posting a lab assignment for you. So look for that as well. Anyway, I hope you guys have a great April 1st. I hope you guys get your family members real good. Get some good pranks on them. Everybody loves that, especially when everybody's so close together all the time. Anyway, yeah, have a good day. Talk to you later.